which is the topic is enthalpy, which is the same as heat of reaction. Heat of reaction being a general term for system changes in chemical systems. And there's a variety of energy changes that can take place, but the general term is heat of reaction. As I said, it's the change in the internal energy of a system, and its definition is the change, or the delta energy. The change in energy is equal to the final energy minus the initial energy. Okay, so that's what the definition of enthalpy is. Just a couple of things then in relation to these chemical reactions. When a chemical reaction occurs in an open container, heat flows between the system and the surroundings until the two are at the same temperature. This can either be endothermic or it can be exothermic. If energy is taken into the system, it's endothermic, and if energy is released, it's exothermic. As we've already stated, the change in enthalpy, or the change in energy, is equal to the final minus the initial energy. And just also to say, for an endothermic reaction, the final energy is greater than the initial, and for an exothermic reaction, the final energy is less than the initial. So you have your change in energy is negative, and in the other case it's positive. Okay, looking closely under the microscope of this question then, we're given 12.8 grams of hydrogen. That's specifically given here in this question. But we see in this equation that we have here, we've got a change in energy for the reaction of minus 184.6 kilojoules, and you also notice that it's negative right there, which means it's an exothermic reaction. And also, as I've said, it's the change in energy for 1 mole of H2 and also of Cl2. But look real close here. The molar mass of hydrogen is actually just 2.02 grams per mole, whereas we've actually got 12.8 grams of hydrogen, which 12.8 grams is in excess of 2.02 by about 5 to 6 times. Now what that means is that our energy released is going to be much higher, because that's just for 1 mole, but we know that we've got in excess of 1 mole, and so we have to bump it up. And right there is where you see it. The number of moles, we've done the calculation on it. We've taken that 12.8 grams from above there. We've done the divvy of 2.02 grams per mole. And the final answer for that then is 6.34 moles of hydrogen. So this energy is going to go up by 6 times, 6.34 times in actual fact. And there below, that's actually it perfectly worked out. 6.34 moles, which we got from above here. 6.34 multiplied by 184.6 kilojoules, which is negative, and the final answer is minus 1170.4 kilojoules of energy released with 12.8 grams of hydrogen reacting with excess chlorine. Okay, in the next question, without even reading, I've just highlighted some important points. First of all, we're talking about working out the volume of a gas, CH4. Given, I skip on to, we're given a pressure of 0.98 atmospheres, which is going to be important in this. And the other thing is that I'm looking at the formula that we're using for working this out, and we see that we've got one of the elements in the formula is N, and N stands for the number of moles. So given those 3 important bits of information, it's obvious that we have to use a different formula that we've had up to this point. So that's why we're using this formula, PV is equal to nRT, because it combines all the information. P stands for pressure, and we're given pressure from here. N we are going to get because we're going to work out the number of moles. Volume is what we need to find. I think we're given temperature at 25 degrees Celsius right here, so we have T. And R is a constant value which is given here at this point. So pretty much we have everything except we have to work out N, the number of moles. Also, we're given our enthalpy change, or energy change in the reaction, which is a value of minus 890.3 kilojoules. It's a negative value, which means that we're talking about an endothermic reaction. And also we're talking about the fact that this is an energy change for 1 mole of oxygen in this case, and that's the energy change. So again, we have a reference to moles, which means we need to work around moles to get the value for N. Okay, what about this then? This 1 mole of oxygen releases 890.3 kilojoules. We're trying to calculate from the question the release of 1 by 10 to the power of 6 kilojoules of energy. So this is the total amount of energy. This is the amount of energy per mole. So it follows that if you divide the smaller number into the larger number, you're going to work out the total number of moles that are needed. In turn, this value for the number of moles is going to be the value for N, which is going to be the N in our formula below. Rearranging our formula then so that we have volume on the left and all the other terms on the right, we just simply insert the values for each of these into the formula, multiply and divide the pressure, and we get a final value of volume 28,000 and 43.3 litres, and that's our final answer.